Welcome to Chapter 3, Section 1. This chapter is all about atoms and the history of atoms. And whereas last chapter we really talked about matter, now we're going to really get into the atom. And we call it atomic theory, and you are going to see a lot of laws. All right. If you love history, well, this is your lucky day because this is like the history of the atom. So let's go way, way back in the days of Democritus, who was a Greek philosopher that first came up with the idea that matter was made up of atoms. And we kind of already have mentioned this before, but atoms are just the building block of all matter. And that was kind of what was thrown out there back in the Greek and Roman days. That no matter what you have, and again, they didn't know about all sorts of matter, but everything is made up of atoms. Now, once scientists had, or once these ideas were kind of thrown around, then chemists started looking at different ways things were coming together. And back in those days, 1700s, 1800s, they could really only weigh things and check out their proportions. And so by doing that, the first law that was kind of developed is this law called the law of definite proportions. And this is one of those things that is kind of intuitive. For example, let's say I have a block of salt from a salt mine. Okay? And let's say I also have, here we go, I'm going to try and draw a salt shaker. Okay? I have a salt shaker. Now, the NaCl in both those examples, the salt in the salt shaker and the salt from the salt mine, a big block, they both have the same proportions by mass. And so if we look at this, the way we define this law, and this is really wordy, right? Chemical compounds always contain the same elements in exactly the same weights by mass. So for table salt, no matter what it is, no matter what the source is, it's 60.67% chlorine, and 39.34% sodium. And that doesn't matter if we have the teeny tiniest grain of salt, all right, or if we have a bucket full of salt. It doesn't matter. Both those are going to have exactly the same proportion, right? Here's another compound that's very familiar to you, water, right? Now water, as far as proportion, works out to about 88% by weight of oxygen and about 12% hydrogen. And that doesn't matter if I'm talking about a cup of water, a pool of water, or all the water in the Puget Sound. It doesn't matter, and by proportion it's going to be that way. And that was a very useful realization for chemists, because now they could start coming on with the further laws that is going to give us an idea of how matter comes together. And by knowing this, that it doesn't matter the size, that made things a lot simpler. You can imagine that if the percent by mass changed depending on my sample size, that would make things really confused. So now chemists could start coming together with this idea that they're always going to come, that elements are going to combine the same way by mass, all right? And so then, through further experimentation and observations, scientists were noticing that no matter what happened in chemical reactions, the mass was staying the same. And that led them to develop this next law, which is the law of conservation of mass. And you've seen this before, I'm sure, in some of your science classes. But the law of conservation of mass is simply that you can't create it or destroy it in an ordinary chemical or physical change. Right? Now you may be asking yourself, well, what the heck is an ordinary chemical and physical change? Well, I can tell you that's the stuff that happens in everyday life. What's not ordinary would be a nuclear reaction. Okay? Because in a nuclear reaction, mass is converted to energy. But in a regular reaction, it stays the same. And what's hard for some people to believe, let's say, for example, I've got some wood, and it's a campfire, right? And then we've got some fire. Here's my fire, and we get some smoke billowing up, and all that. Okay. Now, if you took the weight of this wood right here, and you weighed it, and then when all the reaction was over, and you had this pile of ash, here's my pile of ash, right? And I collected all of the gas and soot, okay? The mass would be equal for that one and for this one. And it's hard for people to believe that, but it really is true. It's been proven time and time again. We'll actually do a lab where we're going to measure things before and after the reaction and find out that the weight doesn't change. So here we are. We've got the idea that no matter what sample size you have, the weights of the elements in a compound are going to be the same by mass. And now we know that during these chemical reactions, whether it's a simple reaction or something really spectacular, that the mass stays the same. Then that moves us on to the next law that is coming into play. And this is the law of multiple proportions. And this is really a wordy definition, so I'm going to try and just give you an idea of what's going on. Let's say we have nitrogen and oxygen. Okay? And we know that they combine to make two compounds. Okay? They make two compounds. All right? They knew that there was these two compounds, and they both had nitrogen and oxygen only in them. All right? Now, if chemists took one compound where the nitrogen weighed 1 gram, all right, then the oxygen, it turned out, in the one compound weighed 1.14 grams. All right? But in this other compound, let's see, I'm going to call this compound 1. Compound 1. And then in compound 2, chemists found that 2.28 grams of oxygen was in the sample size with the 1.0 grams of nitrogen. Right? So what we're keeping constant here is this 1 gram of nitrogen. Now it turns out that in this one compound you had 1.14 grams, but in the other one you had 2.28 grams. Well, do you notice anything about these two numbers right here? And this is for oxygen, by the way. What's the relationship between those two amounts? Well, hopefully you'll notice that 2.28 is exactly twice 2 times 1.14, right? And so they kind of determined that in this compound, the formula was NO, 1 nitrogen, 1 oxygen, but in this compound, the formula was NO2. And so by looking at all these different compounds that had two elements combining, you always got a whole number ratio where they came together for that second element. And this ended up being a very big deal, because we're talking about a time in history where chemists didn't really know about the formulas of compounds. They didn't necessarily know H2O and NaCl and things like that. They just knew they had these compounds, and they kind of understood which elements were in them. So this was kind of giving them an idea on what's going on with how the elements are combining. All right? So now that I've tried to explain that, let me give you this very wordy definition. And this is a very wordy definition. And hopefully you can see that this is exactly what I tried to draw there. When you have two elements, okay, in this example, our two elements are nitrogen and oxygen, and they combine to form two or more compounds, right? As I said, compound 1 and compound 2 and compound 1, right? The mass of one element combined with a given mass of the other is a ratio of small whole numbers. This, I'll be honest with you, this part right here, I'm not a fan of. So it's much more important that you can understand that if we keep one of the elements consistent, like in this example we had 1 gram of nitrogen, okay, the amount by mass of the other element is going to be a simple, the ratio is going to be a whole number. And in this case it was 2 to 1. All right. I know it's hard to wrap your head around it. It's hard for me to explain it. But this was really a big deal because now chemists were understanding that elements, these atoms, are combining in whole numbers. And that was a big deal. So let me show you one more example of what I'm talking about. Here's carbon and oxygen. It turns out that they combine two ways. You've got carbon monoxide, which happens to be the gas that is highly toxic and unfortunately kills people every year. And then you've got carbon dioxide, which is what we're exhaling right now. If you look at the two formulas, the oxygen ratio is 1 to 2. And look at the mass of the atoms here. It's 16 grams to 32 grams. Again, 1 to 2. And so that's kind of how this works. Really, really important law. I wish I could explain it a little bit better, but I mean, it's just really wordy. Right, on to our last part. Dalton. Holy cow, there he is. The genius, the legend. He was an English school teacher. This was back when English school teachers were super, super smart. And he played around with science. And what he did is he took the idea of the atom, he took the law of multiple proportions, the law of conservation energy, the law of definite composition, and came up with the idea of an atomic theory that would kind of pull them all together. All right? And there's not a lot of memorization in this class, but this is one of those things I really want you to get into your brain. Dalton's atomic theory. There's 5 points, and I'm going to be referring to those all year long, and so you've really got to have a good grasp of what's going on. Now, he came up with this in the early 1800s, and for the most part, it was right. Now, you got to remember, they had no idea what atoms, they never saw atoms. We're talking about Bunsen burners and basic glassware was all that was invented. And so this was the idea, and it was held to be true for a long time. And in fact, there's only about 2 of these things that aren't really true today for reasons that I'll share with you. So let's look at the first step of Dalton's atomic theory. All right? All matter is composed of extremely small particles called atoms. Okay? So he took that idea from the Greeks that everything's made up of atoms, right? And then he was saying, with this subdivided, created, or destroyed, he was basically saying, you can't break them apart. You can't break them into little bitty pieces. And that was based, again, on the law of conservation of mass. The chemists were finding out before and after the reaction weighed the same. So that's his first part. His second part, all atoms are identical in their physical and chemical properties. All right? So that means a carbon atom, no matter what I'm dealing with, no matter where it is, under what condition, it's always the same. And that, again, was another one. Now, by the way, if I'm going too fast on this, pause the video, write this down. It's important that you get this. His third point seems kind of silly, but different atoms differ in their physical and chemical properties. So what Dalton was saying, and this was important, Dalton was saying that all atoms are not the same. All right? So that a carbon atom is, in fact, not the same as a silver atom. Oops, that's not a very good A. Let me try this. Let me try again. Not the same as a silver atom, right? Whereas before with Democritus, he was just saying, hey, you know what? An atom's an atom. But Dalton said, no, they're actually different in their chemical and physical properties. All right, 2 more. Here's the fourth one. Atoms of different elements combine in simple whole number ratios to form compounds. Now, where did he get that from? The law of multiple proportions, right? That is a direct relationship to that point. And then the last one. In chemical reactions, atoms are combined, separated, rearranged, but never created, destroyed, or changed. Now, what is that exactly? Hey, that is the law of conservation of mass. So you can see by taking all those laws that were developed before him, he came up with this atomic theory. And again, most of this is still true. Now let me kind of show you just a few things that aren't true because of Dalton not knowing what was going on. But it turns out this one right here, the second bullet, are all atoms of a given element are identical. Well, we have these things called isotopes. And you might have heard of carbon-14 or carbon-12, okay? It turns out that atoms can have different amount of neutrons, but this is back when they didn't know about protons, neutrons, and electrons. Okay, so this one's not really true today. That's okay. And then let's see, can we destroy atoms? Absolutely, but you have to have a nuclear reaction. Right? So there you go. A lot of laws. If this, if this is history's your thing, this is a little bit of history. It's going to be a little more history later on. Hopefully, this stuff makes sense, and we'll spend a little time trying to get it in our brain. Spend some time learning what Dalton said. Try and understand the laws, and I'll see you in class.